Now we're going to start with GPU architecture 1. Now I intentionally selected GPU architecture because in some sense GPU architectures are easier. Then the optimization that GPU applies are more intuitive. So we're going to talk about GPU architecture. Now I'm going to mainly take 3 lectures for GPU architecture. And although the second and the third will probably give you some preview for what's going on in the rest of the semester, that some details will be discussed in the rest of the semester. But they're only previews. They're rather relatively easy concepts there. Okay, I will explain those in the second and third lecture. And later on, when we talk about CPU, we'll see how a more complex version is implemented in a CPU. So let's give a quick review and talk about parallelism. So last time we talked about sequential logic, right? So in sequential logic, every circuit element is either a register or combinational logic. Then at least the one circuit element is a register. So there are registers, and all registers receive the same clock signal. Every cyclic path contains at least one register. So that's a simple, very simple sequential logic. And if we use a state map, what we're basically designing is what is shown at here. One group of register, a few bits, a combinational logic, right? So since we're saying with kernel map, we probably can only do like 4 variable, 4-pin, 4 wires optimization. So our register can only have 4 values. That's the limitation that we can do hand derivation. But in reality, things are much more complex. In real hardware, there are just a ton of combinational logic, a ton of registers. Then it's just not as simple as one register and one combinational logic. Since there are so many combinational logic, and if you consider this, if there's a clock signal, if the register updates its data, all this combinational logic will automatically trigger, automatically calculate the result for the next cycle. So there creates an intrinsic conflict. Then for human understanding, then this is a code that we write. There's an if statement, there's a for loop that we do first thing, then we do second thing, then we do one after another, right? This is human understand the word by sequential. Like we do this first, then do next, do next thing. But so human has a serial thinking or sequential thinking. Now, but digital circuit has parallel execution. There are so many combinational logic, and those combinational logic can do calculation and do logic operations at the same time. So if we only do one instruction at a time, say there's a add operation, for example. If there's an add operation, then we're only using one combinational logic. We're wasting all the combinational logic and the registers in our whole chip, right? So then pretty much for the whole rest of this course is about addressing this conflict. It's about how we can write a serial program, at least a program that human can understand, then use some either programmer aware techniques like GPU programming, or some programmer transparent methods like how CPU is optimizing the code to achieve parallel execution. Okay, so there are different methods to support parallel execution for a serial program. Now we call this parallelism, different type of parallelism. For example, there is just different ways to use hardware, parallel hardware. We have task parallelism that may do like this more easy to understand, right? One program is a browser, one program is a word processor. They're doing different tasks and they can run in parallel. That's okay. Now we have data level parallelism, thread level parallelism, and instruction level parallelism. So for GPUs, we're going to talk about data parallelism, data level parallelism, thread level parallelism. And for CPUs, we're mainly going to talk about instruction level parallelism. It doesn't mean GPU doesn't use instruction level parallelism. We'll talk about how GPU use instruction parallelism in Thursday's class. But mainly GPU uses data level paradigm and thread level paradigm. And also, if you consider CPU, early days prior to 2000, right? By that time, everyone thinking, oh, we just increase frequency, then we can get really, really fast CPUs. Now, what happened is when the frequency is just getting too high, they just realize it generates too much heat, then there's no way just to continue the performance scaling. There's no way to continue improve the CPU performance by increasing frequency. So what they are doing is just introduce the multi-core CPU, right? So what paradigm is multi-core CPU is utilizing is pretty much task paradigm and thread paradigm, thread level paradigm, right? And also you can also say there's data level paradigm in those cases if the program is suitable. Okay, so CPU and GPU utilizing this type of paradigm in different ways, in different levels. GPU cares more about data paradigm and thread level paradigm. CPU cares more on instruction level paradigm. And I intentionally didn't write data paradigm. So data level paradigm and data paradigm, typically there are two words in different scope. Data paradigm is a machine learning training terminology that we use multiple GPUs to do training, then the data is aggregated together. And when we talk about data level paradigm, it's more like a microarchitecture concept that we talk about how the internal threads and the data are organized. Okay, so we understand the paradigms that's showing a very simple example. That's a vector add example. It's element-wise vector add. So we add each element together to get a result. And if we write a C program, I think you should be rather familiar with this type of program. Even if you have never written a C program before, you should probably can understand the syntax. Right? Even if you have only write Python before, it's just syntax is slightly different, but there's a for loop. Start, let's say, okay, n equals to 8. It's just 8 elements. Now floating point arrays A, B, and C. Then we do an element-wise vector operation C equals A plus B. Then from I equals to 0, I smaller than n, I plus plus, then we add each numbers together. Then at the end, we use the result, we print the result, then we free up the data that we allocated. It's a very traditional C program, right? And the core part is this for loop that we repeatedly doing one thing. Now, what's the characteristics of this for loop? The most important part is the calculation of each data point is independent. It doesn't matter which one we calculate first. So we can always calculate the first one and the second one. So they are independent. If they're independent, we call this is a particular pattern that is called embarrassingly parallel program. So what is embarrassingly parallel? That means it's just so easy to parallelize this program because every element is independent from each other, right? So this is called embarrassingly parallel program. Then if we see this type of program, we're pretty much sure if the data size is good enough, then we can use a GPU to improve the performance. And for most of the case, our program are not embarrassingly parallel, then that will require some techniques to make the program parallel. But actually, in our real world, lots of programs are embarrassingly parallel. So let's see how we can parallelize this program in C. In C, we basically use this library or this technique called pthreads. Then we can start multiple threads to write a program, right? So how we started, the beginning is exactly the same. And we start n threads. Here we only declare these threads at this moment. And in a for loop, we create these threads, right? We create these threads and which thread it is and what's the function. And this is a function pointer and what are the arguments that pass to the thread. Then, so here is launch one thread per data element. And here is the thread program. So if you look at this thread program, it describes the behavior of one thread, right? It describes the behavior of one thread. So we first get argument, then we get t arrow I, t dot I. So we get which particular element it is. So the thread needs to have some self-awareness so that it needs to know which thread it is, which data it needs to process. Then we do CI equals AI plus BI, and we return now. We're good to go. Okay, good to return. So at the end, we need to join so that we guarantee that all these programs are completed because the main thread keeps going. And if we don't synchronize at this point, we may just fall through. Then when we use the result may not be ready. Then we can get some garbage data. Okay, so on piece of paper, this is a good design because we can parallelize the execution of every element. And in reality, this is a terrible design. Why? What's the problem with this program?
Yeah. Well, it's ultimately going to be slower because the task that each thread is doing is simpler than all of the tasks you're doing just to create that thread.
Yeah.
Right. It's just one array, like one element of one vector. So it's if you wanted to parallelize this smarter, you could say, okay, each thread does like some number of elements of a very long array. Like it does 4096 or something elements.
Yeah. That's right. So there are too many threads. Then allocating one thread there's some overhead. There's some calculation instruction level overhead. There's also some memory overhead. If we have a really large array, the number of threads may just explode your memory. So don't do this. Then think about how many cores you have. Then allocate basically roughly the same number of threads as the number of cores you have. Definitely no more than 2 times of the number of your cores in your system. Then allocate a group of them and run them together there. Okay. So, but I just want to show you, this is the typical way that how we think about a parallel program. So what's the key point here is basically we need to find the embarrassingly parallel patterns or find the independence. Then no matter if it's CPU or GPU, we want to find output, take the output. Then we consider one task is to calculate one piece of output. Then we can parallelize the computation of each output element. Okay. Then let's talk about the need of parallel programming. Then when we talk about parallel programming, we have to talk about matrix multiplication. So why matrix multiplication is so important is because machine learning, right? So we all know machine learning. In machine learning's program, this is my personal brief estimation. Okay, I would say 70 or 90% of calculations in machine learning workloads are pretty much matrix multiplication or similar operations. Think about a fully connected layer, like neural network. A fully connected layer is a matrix multiplication. Then convolutional layer, even a convolutional layer, they're doing some operation called image to call. Need to convert an image into a matrix so that they can use matrix to perform the operation. Why they just don't do convolution directly with a loop? Because our devices are so optimized for matrix multiplication. So doing the extra step to do the conversion is actually worth the time. The overall performance will even be higher. So convolution, then transformer, you probably have heard of transformer. Transformers, a major part of transformers are fully connected layers, the feed forward the network, FFN. Right? FFN are matrix multiplication because it's pretty much basic neural networks. So it's matrix multiplication again. Now, if you look at matrix multiplication, how we get this point? How we get this point? We have this. Where's the pointer? It's on the other side. Goes with the mouse pointer. So how do we calculate this one?
You have to use the column from the first column from the right matrix.
Yep.
Or the first row.
It's the row here and the column here, right? So then, okay. Then the question is, does the calculation of the second point really matters from the first one? No, right? It's totally independent. So we can just calculate the first one and the second one together at the same time. And so can we say this is an embarrassingly parallel program? Pretty much at this stage, yes. Then if we dive deep into GPU programming, almost we never want to write in that way because we want some extra performance optimization. Because if we calculate the first one, we're loading the whole row. Now, if we're calculating the second one, we're still loading the whole row. If you just consider they're totally independent, we're loading this row multiple times, which is something that we don't want. But at this stage, don't think about that level, or don't think about optimization. Like if you just want to write a GPU program, just write each thread to calculate one cell. Okay, then that's good enough. So if you consider the output matrix can be very large for machine learning algorithms, then there are a lot of opportunities to do this parallel execution, right? So today, if you do some GPU research, you should always verify if the GPU architecture improvement can improve matrix multiplication performance. If your design can improve matrix multiplication performance by 10%, but slow down everything else by 5%, you are very good. If you improve the performance by 10% of everything else, but slow down matrix multiplication, nobody will accept that one. Okay, so matrix multiplication is just that important for GPU. Okay, then let's talk about GPUs. GPUs are originally designed for graphics, right? So how graphics works? Graphics works in this way. So when user write a GPU program, let's just say it's a 3D game, right? How they define something? They define, okay, here's a body, here's a car or something, right? Now, an object. An object is organized in a mesh of triangles. Just triangles, right? Lots of vertices then connected with triangles. So we use a process called vertex shading. When we talk about shading or shader is basically a something. I just call it something because if you talk about software, it's a piece of software that can compute. Now, if we talk about hardware, it's a piece of hardware that can compute. So I'm just saying it's something that computes the color or other properties, say where it is, the lightning strength, or how far away from the camera this element is of something. What is this something? This can be a vertex or a pixel. Okay, so we calculate the color of everything, right? Then we do a rasterization. Basically, we convert into pixels. Then we do a pixel shading. We calculate the number of the colors of each pixel, and we combine them together, and we render the final output. Okay, so if you consider how many vertices are there, it really depends on the game. If it's a Minecraft game, it's probably not a lot of vertices. If it's like a really high-end 3D games, really resource demanding, it can go up to 10 million or even more vertices. Now, about the number of pixels, that's a relatively fixed number for at least for this stage output, right? Even for this stage output, there may be wasted pixels because it's hiding behind. But for the final output, it depends on if you want to render like 1080p or 4K gaming quality. In this case, it's a few millions. Now, in recent years, so if we're talking about rendering, we have to talk about ray tracing. And how ray tracing works is basically we have the object or a lot of objects in the scene, and we have a camera. What we're doing is we cast the rays out of this camera. Then we calculate the refraction and reflection on the objects. Right? We calculate, say, it first go through a pixel. In this needs to go through this pixel. Then it goes here. Then probably reflects to a light, or it probably reflects not to a point that is not a light. Right? So we just scan the whole scene by generating many rays. Then to calculate. Let's say eventually how many rays can you land on a light source and how strong the light source is, right? Then eventually we can infer how bright a pixel is, right? So other than the super large number of vertices there and triangles there, we have 10 to 100 rays per pixel per frame, right? So one frame, if you consider if you want to play a game at 60 Hertz, is 60 frames per second. So you need a large number of rays per pixel so that this pixel can be realistic. Then, so that's a few million rays. And just consider every ray. You go there, you probably need to consider, oh, is it contacting this surface? Is it contacting that triangle? So you need lots of calculation. So lots of calculations. And if you consider this type of calculation, every calculation on the vertices and on the pixels are independent from each other, right? And every ray here in this case are independent from each other. So rendering is intrinsically an embarrassingly parallel program. So GPUs are originally designed for embarrassingly parallel program. It can just calculate these things many, many times with much larger throughput, with much larger computing capability. So then it was machine learning people that they really, really need matrix multiplication and high computing power. And they realized their programs are highly repetitive. So they just starting from around 2010, then they start to use GPUs to run programs. Then at the early days, there's no compute program. There's no programming framework that is just designed for computing purposes. They just use these type of shaders as if they're calculating colors. Then later on, really by that time, they use OpenGL to calculate machine learning programs. And it's really awkward by that time. Then CUDA comes out, OpenCL comes out, computing frameworks come out. It's just more natural today to use GPUs to write general purpose computing applications. So everything that we talk about GPU are general purpose computing in this course. We're done with rendering. Okay, let's talk about GPU programming. Still many things before we can really talk about GPU programming. So first thing is we need to talk about this concept called host and device. So what is a host program? A host program is a piece of program that runs on the CPU. Just consider the pthread program. It's the main function, it's the host program. It's what bootstraps the whole program, initialize the data, and eventually consumes the data. Now, on the other side, we have the device program. It's a program that runs on the GPU side. Okay, so why we need a host program and a device program? So GPUs, although they are very powerful, they are really limited, right? They cannot really access hardware, network, hard drive. They cannot respond to or take in user input on the generated user input to anything else other than the screen. Okay. They need CPU to tell what to do. The CPU needs to coordinate. And the GPU is super slow in single thread program. So sometimes your program really have no single thread parts. So you still want to move those parts to the CPU side. And CPU today is actually very powerful. Wasting the CPU resources is a waste. So GPUs are only accelerators. Okay, so don't think they are powerful devices that they can do anything. They're actuators. What are actuators? That means a CPU offload part of the program that is really compute intensive. Then the CPU can still do it. It's just not fast enough. Then the CPU offload that part of the program to the GPU side so the GPU can run it faster. Okay, so there's an offloading process. GPU is only an accelerator. So how we can program host and devices, like we said before, there are a few programming frameworks. There are even more things these days. CUDA is NVIDIA only. NVIDIA started CUDA. And CUDA is the most important resources for NVIDIA today. People use NVIDIA devices mainly because of CUDA. It's a very, very mature, easy to use. Still not very easy to use, but better than other things. In ecosystem, right? There are profilers, debuggers, and many, many other tools. So the host is pretty much a regular C or C++, and the device can be CUDA C is a C-like code. And just don't think CUDA is only about C and C++. CUDA can also support Fortran. You may think, why Fortran, right? then you probably underestimate how many people are still writing Fortran. Then lots of my collaborators and friends, like especially people from NASA, write like the weather forecast programs, high performance computing applications, they still use Fortran and they really like Fortran. So CUDA supports Fortran and can parallelize the Fortran programs. Then OpenCL. OpenCL comes out pretty much around the same time when CUDA is out, like around 2010, 2011, 2012, that era. It's an open standard, then a lot of companies support it. Mainly it's supported by AMD, but it's interesting that OpenCL trademark is owned by Apple. But Apple somehow supports OpenCL, but never very well. Okay, then Apple, what's the program framework for Metal? I said it. So Metal is the programming framework for Apple, right? So Apple has their own programming framework other than OpenCL, and is tightly integrated with their ecosystem. And if you have program OpenCL, I learned the GPU programming with OpenCL. Now I know CUDA, and I never want to go back to OpenCL anymore. It's very verbose, very annoying. Then AMD deprecated OpenCL and start to write something called heap. I guess they really wanted to use CUDA directly, but because it's owned, the intellectual property owned by another company, they just cannot use CUDA again. So they started something called heap. So heap is very, very similar to CUDA. That if you know how to write CUDA program, pretty much you know how to write a heap program. It's just a search and replace thing. And actually, AMD provides a program called Heapify. It can automatically convert CUDA program to heap. Then these days with generative AI, probably you don't need Heapify anymore. Then generative AI can do converting even better. Okay, so 3 main program framework here, and there's something more. Have you heard of Triton? So Triton is a programming framework for developed by Meta. Then it's a programming framework intentionally designed for machine learning algorithms, like matrix multiplication style programs, and it's in Python. So in Python, that means it's much easier to program, and it's called a tile-based programming language. Okay, so if you're writing something for machine learning, that if you want to write a kernel on your own, I highly recommend you learn Triton. Okay, check Triton, see if it's a better choice. Then it has many useful features like performance automatic performance optimization. It will test the different styles of how these kernels are compiled to a GPU program on this particular GPU. Then select the best one to run there. Okay, these features are impossible for CUDA. But we're not going to talk about Triton. We're going to focus on CUDA for this course. But if you write a GPU program today, definitely consider Triton. Okay, and even if you know Triton, you probably need to understand some basic things from CUDA, the basic concepts from CUDA. Okay, then talking about memory model, then how memory works. So for CPU, if you have built a computer before, if you have a CPU, you need to buy memory on your own, right? So memory you buy on your own are called DIM. I really want to call it direct insert memory module, but it's still, I don't remember what's the I there. The deal here means the pins are on the 2 sides of the bottom on the PCIe bus here. So the pins are on 2 sides. Previously is SIMM. That means it's only on 1 side. Then DDR, don't get confused with DDR and DIM. DDR stands for double data rate RAM. Okay. RAM is read access memory. So what is double data rate? That means it can perform read and write, perform read and write operation on both the rising edge of the clock and the down edge of the clock. So it can do 2 actions per clock cycle. Okay, this is DDR. Then DDR are typically used for CPUs. Then for GPU, then the story is a little bit more complex. Then if we take a GTX 5090 GPU and we take the shell off, what do you call this? This is a PCB, right? Printed circuit board. Although you probably cannot see the board anymore because it's full of devices, but this is the PCB. Then the GPU is very clear. It's the biggest part. So by the way, what's the difference between this one and this one? They're both GTX 5090. Yeah. Cooling? Yes. Cooling is different. This one, if you cannot see from outside, there are 2 fans. This one has 3 fans. But most importantly, this is produced by NVIDIA. Okay, this is produced by ASUS. So it's just a different manufacturer. So ASUS basically buy this thing, the chip there. It buys the chip from NVIDIA and produce. They have their own PCB, they have their own shell, they have their own cooling solution. So the chip are pretty much the same, but the external solutions are different. So they may have different performance, slightly different performance due to probably more powerful cooling and the slightly different frequency setup, but they're essentially the same chip, very similar product. So they may sell at different prices. So this is the chip, right? Now where's the memory? Yeah. Those are the chips surrounding the main memory, the main chip, right? Those are a lot of chips. So why there are so many? Because they wanted to run in parallel, right? They read data and write data in parallel so that they can provide the throughput. So what's the technology here? It's still basically double data rate run. But GDDR is optimized for GPU, for graphics. This is GDDR memory. GDDR memory are separate chips that also, even this is produced by NVIDIA. NVIDIA buy from other vendors. Okay. Okay. So this is H100. Where's the memory? How many memory modules are there? So who say these are memories? Now who say these are memories? 6 pieces of memories. Okay, 1, 2 versus 1. Okay, the correct answer is these 6 units are memories. Okay, so I don't have this, but this is a rather advanced packaging solution. Now, how this packaging works is you can say this is a chiplet technology. What is a chiplet? Chiplet is basically in one product, we have multiple chips. Now, multiple chips, in this particular case, there's only 1 GPU chip, but there are 6 memory chips. And so how does chiplet technology works is on the bottom, this is called a substrate or interposer. Substrate is the base of the semiconductor, right? Is in the manufacturing, they just call it substrate. Sometimes there's a separate interposer layer, but I will just write this as substrate or interposer. Interposer. Okay, so they put chips on top of it, but at the bottom of the chip, There are pins. Okay. Then these are HBM memories. The HBM memories are very special because HBM memories are stacked. High bandwidth memories are stacked. Okay. So why H100 use HBM, but GTX 5090 use GDDR? As the name suggests, this one has higher bandwidth, but two cost in two different aspects. First thing is the latency for high bandwidth memory is higher. So it takes longer time for the data to return. They just need to go up and get the data and return. Okay, and the protocol are slightly different. So the latency for HBM are higher. The second cost is HBM is super expensive. So they can only afford it in the most high-end compute-oriented GPUs. For GDDR, it's have some balance in the compute, in the latency and the throughput. So it's optimized for graphics. In graphics, you really need to consider latency, right? Because if you really want to see that frame in 1/60 hertz, right? You really want to see that frame on time. If it's not rendered on time, then it's not useful at all. So here are the memory unit. Okay, but the main story is the CPU memory and GPU memory are totally different things, and they're not together. If they're not together, we just simply write GPU memory. That means we need to do a memory copy. The CPU will prepare the data, copy the memory to the GPU side. GPU perform the calculation. Then once done, then put the memory back to the CPU side. And for a machine learning algorithm, if you think the most of the data are the weight or the parameters of a model, right? So at the beginning, you can copy the data to the GPU side and then can stay there. Now they say LM, right? The parameters of the model are there. Then you just feed in the user input, and it would perform one calculation. Then the final output can come out from the memory copy. Okay. And as we said before, there's one problem. DDR are cheaper. HBM, if you really want the high bandwidth, are very expensive. So don't expect GPU to have super high memory, super large memory. So what's the largest memory for GPU today? How large is the largest GPU memory? 64 is close. The correct answer should be 80 gigabytes for H100 GPU. So the range estimation is pretty good. So 80 gigabytes of memory. Then if you consider some models have 700 billion parameters, right? That means pretty much we have no way to put those models in one GPU. What we can do? We have to use multiple GPUs. So today, one server may have 4 GPUs or even 8 GPUs. Then it's not really, sometimes it's really not because we need a lot of computing power. It's really because we need the memory capacity. Before LM era, that's hard to imagine because by that time, GPU memory is not the limiting factor. In 2015, I was using high-end GPUs with 4 gigabytes of memory. Today, 80 gigabytes is not good enough. Okay, so this is how GPU works and GPU memory, but to solve this memory problem, then these vendors start to create unified memory system. Then GH200 is one of the, GH200 is Grace Hopper. The NVIDIA name is Grace Hopper because their CPU die, the CPU chip is called Grace chip, and the GPU is the Hopper chip, right? So the Grace Hopper, then you can see the CPU may have some memory on the side, but the GPU may have the memory here. So it's not a pure CPU and GPU unified memory system, but their addressing system are unified. So the GPU can theoretically accessing the CPU memory directly, but probably at a higher cost. Then AMD MI300A is another GPU that you can see. This is a more fundamental chiplet technology. So what is chiplet technology? AMD is very good at chiplet technology. Even today, NVIDIA is not really using chiplet technology, right? So AMD is having 6 XCDs. They don't call it GPUs. They call it the accelerated compute die. And CCD is core chiplet die. So basically this red part is the CPU and the blue part are the GPUs. Okay, and where's the memory? It's basically here on the side. Okay, so AMD has a more fundamentally unified system. Then, although there are still some NUMA effect. What is NUMA effect? NUMA stands for non-uniform. Memory access. NUMA. Non-uniform memory access is actually a very, very interesting research topic, and it's always a research hot topics that say these CPU dies may access this part of memory faster because it's physically closer, right? So if this part of this GPU wants to access the data here, then it takes longer time. Then there's always a problem that where you put your compute, then where you put your data, then it's always research questions. Okay, now if we talk about unified memory, we also have to talk about Apple. So this is Apple M3 Ultra. Then it's just a little bit hard to tell which part is the CPU and which part is GPU. I guess the top part is the CPU and bottom part is the GPU. Then the memory are not integrated and they're not HBM. They're not DDR. They're a Apple adaptation of low power LP DDR. But Apple just totally changed it. So it's not a standard. And then they produce in one package. They're also not using something like an interposer. They just use thin connections, wire connections across them. It's not even on a PCB, but it's not also not on these type of things. So Apple is always doing Apple things. Then this is also a pure uniform memory system, right? So CPU and GPUs are all together. So what's another advantage of unified memory system is that we don't really need to specify, oh, this GPU, this part of data wants to allocate on GPU side, this part of data on the CPU side. And we also don't need data movement. We don't need memory copy. We just do a malloc, regular CPU malloc. Then we can use it on the GPU side. Okay. So then let's see. Vector I think could. Yeah. Yep. Okay, for unified memory, we can talk a little bit more on unified memory. So there are different types of unified memory. So even today, just regular NVIDIA GPUs, they support unified memory. Even regular NVIDIA could support unified memory, but their unified memory is managed behind the scene. So what's happening is, let's say the GPU, right? The GPU wants to access a piece of data. Then they're doing a address translation process. We'll talk about address translation later. And then they realize, okay, the data is not here, right? The page is not here. What they do is they can allow two different things to happen. They can just say, oh, you want this data, let's just give it to you. Now this happens at the granularity of a cache line. So typically 64 byte or 128 byte, a very small granularity. But if you consider PCIe latency, that's thousands of cycles. just to get one piece of data, thousands of cycles. Another way is even more drastic. They say, oh, this GPU really wants this data again and again. So providing this data from remote again and again is not very efficient. We should move the whole data to the destination, right? To the GPU side. So it's a page migration. So we migrate a page. Typically, CPUs are used 4 kilobytes. On GPUs, it can be 16 kilobytes or even larger. Then they migrate the whole page to the GPU side. But if you consider migration is actually very complex. Then a lot of things need to be paused and reset. Then the data copy takes even longer time, so it's a higher cost. So eventually the driver and hardware decide if it worth the effort to really do the data copy, the page migration to the GPU side. So if say there's real page migration, there's real data copying happens, I would say a more precise way to say is page migration or data migration. Okay. I don't see in product devices that they really allow something like duplication. So when you say copy, it's a duplication. So this piece of data resides in 2 different locations. No duplication, just data is moved, so it's destroyed on the source side. So on GH200 probably is more likely to take the first way because they think, oh, the bandwidth and the link between the CPU and GPU are so good that we can just access the data. But I guess there's still migration happening in GH200 because you can see there are still different technologies for the memory, right? But for Apple and for AMD, it's more likely to be really accessing the destination directly. They say just no page migration happening. They say if this GPU core needs to access data here, then just access. Just go through this memory interface on the side at this point and directly access memory. So the CPU and GPU just share the bandwidth. There's really no difference between the CPU memory and GPU memory. Okay, so different product may have different solutions to address unified memory. Then from discrete NVIDIA GPUs to GH200, MI300A, and Apple III Ultra is on a spectrum from the most disaggregated way and the most aggregated way to manage unified memory. Still, today, if you write something like, if you have a device like there's two high-end CPUs and 8 high-end GPU, 8 H100, for example, you probably never want to use unified memory because the performance is still terrible. For Apple M3 Ultra, you probably should use unified memory because there's no performance difference. And if you do memory copy, there's a duplicated data, there's a waste memory. Okay, so MI3 Ultra is actually quite interesting. MI3 Ultra has the largest one has 512 gigabytes of memory, which is much higher than what we talk about, the 80 gigabytes of H100, right? And also M3 Ultra on Mac Studio is about half the price of H100. So it depends on what you want to do. So for memory intensive workload, and if you really require a lot of memory capacity, but memory bandwidth is not that important, buying M3 Ultra to do like inference for you, something like DeepSeek 661 billion parameter model doing inference, the M3 Ultra is probably a good choice. If you want to do training, still go with NVIDIA or AMD GPUs. Because training probably needs more memory bandwidth. Okay. Okay, let's talk about vector add in CUDA. Not something exciting, but just program. Okay, I put pthread on the left and the CUDA program on the right, and we can see they are very similar. At the beginning, we include. So in pthread, we include pthread. It should also include this standard I/O. And here it includes CUDA runtime, which replaces the pthread. And let's see how we write the kernel code. I call it the thread code or the kernel code. It's vector add, right? This is a vector add thread, and then here we just call it a vector add. And there's a modifier or descriptor of this function. Now it's dash underscore underscore global underscore underscore. And whenever you see a 2 underscore before and 2 underscore after, that's a CUDA preserved keyword. Global means it can either run on the device or can run on the CPU. Okay, and can be launched as a kernel. Then, okay, then we have parameter list. And pthread is much more annoying. It can only accept one argument thread. CUDA is more smart, and that we can accept the A, B, C, and there's actually an N, the total size of the array. But the screen is not wide enough, so N is not included. Now on this side, we need to build a self-awareness. What is the ID, thread ID, right? Who am I? On this side, we also need a thread ID, TID. We'll talk about this calculation later. But here, basically, this TID is equivalent to the I on the other side. Okay, now we do a boundary check. We'll talk about why boundary check is necessary here. Then they say, well, there may be more threads than N, right? So extra threads simply do not do anything, but it will perform CTID equals ATID plus BTID. Then it will they will return silently. Okay, it's a CUDA program. It's rather straightforward at this stage. Now on the CPU side, at the beginning, there's nothing special. We have a data. We have the data pointers arrays. But remember, we're doing memory copy, right? So we need to have multiple data pointers. So for ABC, sometimes you can see pointer start with H that stands for host, right? So by here, we just name it at ABC. As a convention, if a pointer starts with D, that means these pointers are supposed to be allocated on the device side. Then we use regular malloc to allocate the data and initialize the data. Okay. Now here, this is something that only exists on the GPU side. On CUDA side, that we have CUDA malloc. So if we use CUDA malloc, this data will be allocated on the GPU side, not on the CPU side. Then we do CUDA memory copy. CUDA memory copy. So there are a few parameters, right? The first one is the destination. DA is the destination. Then A is the source. Then how many bytes that we want to move, and multiply by size of float. Float is single point, 4-byte or 32-bit numbers. Now, at the end, we need to specify what's the direction. In this case, it's CUDA memory copy host to device. Later on, you can see it's device to host. It's copying data back. Yeah. Very likely, if you directly write into DADBDC, you will get a segmentation fault. Okay, then we launch the kernel. We start the threads. Here, we have a special syntax that uses this 3 triangle bracket. Okay, so it requires 2 extra parameters. One is called the number of blocks, or I just call it kernel size. And the other thing is the block size. We'll talk about that later. But when they multiply together, they just equals to the total number of threads that we want to launch. Okay. Block, using the design of block, is something that GPU is constrained by the hardware capability, that they have to introduce this awkward concept called block. I guess they really don't want to introduce this concept, block concept, because it's add one extra layer of complexity, right? But they just have to let user to define what's the block size. We'll talk about why blocks are used next time on Thursday. The DADBDC and N, right? Arguments, nothing special. So once we call it, it will start running. Then it will automatically spawn so many threads, can be millions, billions of threads, and there's unlimited number of threads that we can launch per kernel. and it will just run until the result comes out. Okay, the result will write in the GPU side. So here there's a equivalence that on the CPU side, we're doing a synchronization here. So there's still the main thread, right? The main thread will keep going without waiting for the subthreads to finish. So we have to use the join method to synchronize. On this side, you can use CUDA memory copy as a asynchronous, synchronous version. That means the calculation before this point has to complete, then we can start to copy the data back. So this is a synchronization, then we can copy the data back from DC to C. Then we use the result in C. The actual step for GPU is to free up the memory, free up the GPU memory. Now, of course, we also need to free up the CPU memory. Okay, so it's rather straightforward. I think the only thing that I didn't explain is the block size and the block size and the kernel size and the kernel dimension stuff, right? Any questions with this code? Okay. Then let's talk about kernels, blocks, and threads. So this is a vector, the vector add kernel. Then the first line is a very important line that in many GPU programs, you will see something like this. So a kernel is a piece of program that describes the behavior of many threads. And for GPUs, the number of threads can be very large. And I would say typically it's rather reasonable, at least much more reasonable to write this type of GPU program to calculate one piece of data per thread. Still, as we discussed on the CPU side, one thread has extra overhead. At least this calculation is not free. If you do this calculation, only do this calculation, and if condition is also not free. If we only do one calculation, but add the actual calculation here, there's still overhead. So it's still more reasonable to at least allocate some number of work, piece of result on the GPU side. So not only calculating one piece of data, but calculating a chunk of data. Okay, but just for simplicity, let's just see this type of GPU kernels. Now, what is a thread? A thread is an independent program that runs in parallel, right? So that means TID, right? TID in thread 1 and TID in thread 2 must be different. So the numbers in the variables that may have the same name, but they have different values. Now, how we can launch a kernel is launch a kernel. We have this specific word called launch a kernel, not call a function or something, invoke a function. It's launch a kernel. Launch a kernel function is basically calling a GPU program or calling a GPU function from the host using this syntax. Okay. So we need to decide how many threads that we need to have. That's the first thing we need to consider. And typically that's the number of output element. But sometimes we also typically write in a way of fix the number of threads. Let's say if your GPU can run 4,000 threads at a time, we just have 4,000 threads. Then let each thread to do more things. That's also a very common way. And in my previous profiling, fix the thread implementation can be a few times faster than the number of than just to have the same number of threads as your output element. It really depends on how large is your real calculation part, right? So this has some, this calculation has some overhead, and starting one thread has a little bit overhead. Then if you only do one thing, that's probably a waste of threads. But if the calculation is already very complex, then the overhead can be negligible, so then it's not that important. So what is a block? A block is a group of threads that can synchronize and communicate. So that means this hints that threads outside one block cannot synchronize and cannot communicate. That means in GPU, you always never write this type of program. What type of program? In one thread, you write while A equals to 0, wait, then do something. Then on another thread, you write a program here, say, do something to B, and this is to A, then A equal to 1, then do C. Okay, in CPU, this is rather common, right? We just say, oh, we have to finish one task, then set a flag, then decide, read a flag, then we continue going, right? We have to wait the result comes out so that we can keep doing calculation. In CPU, this is rather common. In GPU, this can only happen within one block. Okay, so don't expect one thread can tell another thread something. Now, if you really need to do this, what do? Stop the kernel and start a new one. So global synchronization can only be completed at the kernel boundary. There's no way that one thread can wait for another thread. We'll talk about it's because of some hardware constraint that this has to be implemented. This has to be prevented. Okay. So communication can only happen within one block. Then the typical block size is 32, 64, 1024. And we'll talk about this later. So number of blocks is basically the ceiling of threads divided by block size. So if you need 1 million threads and divided by 1024, then that means you need 1024 blocks. Okay. So because in NVIDIA, in CUDA, you can only launch the number of threads that as a multiple of block size, your block size. So all the blocks are full blocks in CUDA. That means you have to have this boundary check. You have to do this condition there so that you don't access out of the boundary. Okay. Then indices. What the indices are here? There are 3 indices that we used at this point. Thread index is the index within the block. So it can be maximum 1024. Block dimension is how large is each block. It can be 32, 64, and 1024. It can actually be any number smaller than the 24, but it doesn't make much sense if you select other numbers. Then block index is which block it is. And first block, second block, and third block, and so on. So block index multiplied by block dimension, that's the total number of threads before your current block, plus a thread offset, and gets a unique global ID of your thread. Okay, that's how you calculate this TID. So I think that explains all the details of this vector add kernel. Okay. Then we're going down to hardware. So I think I basically explained how a GPU program is written. And you see on our GPU programming course, you should learn advanced GPU programming techniques in other courses, but then we're soon going to the hardware, the implementation, how the hardware can support this type of program. So there's a terminology called SIMD, single instruction multiple data, or sometimes called SIMT. Let's talk about this classification of hardware. The most simple type of hardware is single instruction, single data. Now, if we fill this coordinates or classification, we have single instruction, multiple data. Now, on the other side, we have multiple instruction, single data. And finally, we have multiple instruction, multiple data. What does that mean? So let's see examples. A CPU single core is basically what we say, a single instruction, single data, right? We have add instruction, then we just simply add 2 numbers together and get 1 result. So 1 instruction to process 1 piece of data. With a single instruction, multiple data, that means we do an add operation. An add operation is actually adding multiple numbers together, but we only say, oh, there's only 1 add instruction. Multiple instruction, single data is pretty much only in the theory. I don't know any real hardware that implements this. Multiple instruction, multiple data is typically multi-core CPUs or just multiple devices that are just running to different things. Okay. So let's say, let's see how it works. Let's say add instruction. For CPU, then we have this instruction called add R5, R6, R7. R5, R6, R7 are registers, are flip-flops that store in the data. The CPU, when we say R5, in CPU, that means it's only one register. There's only one value, two values at the third value. When on GPU, what we're doing is we say do add, then it's always add in an array of them. So every calculation is in an array. That means this is R5, right? In this thread, R5 may have value 1, and then R5 may have value 2, and so on. Then this R6 may have different values. Then the result may be different values. Okay. Then the advantage is for GPU is it's more efficient in terms of computing because you think about this issuing process. Issuing decides which instruction to run, right? Issuing is actually quite complex because we need to load this instruction from the memory. Then we need to decode it and decide which to run. It's a complex process. Then if we have this whole process and only calculate one piece of data, is a waste of resources, right? So similarly to the concept of like having fewer threads, but to do more calculation, GPU cares about calculation. So GPU wants to maximize the utilization of the ALUs. The ALUs are arithmetic logic unit, are the combination logic can really calculate the data. Question? Yeah, I'll talk about that later. Let's consider CPU, the CPU here in a traditional CPU way. So issue has overhead, so it's better utilization of the calculation, the ALU. So the design philosophy is CPU is optimized for latency. So we want to calculate one result as fast as possible, but GPU is optimized for throughput. I can wait for one piece of data to come out, but I want to have a lot of data to be processed in the same amount of time. Okay, then talk about this. Now you need to consider, that means if I'm executing one add operation, there are multiple threads there, right? So in this case, there are 6 threads that these 6 threads must all do add operation. They cannot do different operations, different instructions at the same time. So what's that concept? That concept is called a warp. Okay, in NVIDIA terminology, it's called a warp. In AMD terminology, it's called a wavefront. I guess I'm going to use NVIDIA terminology today and use AMD terminology on Thursday. Let's see, so that you get familiar with both. Yeah, it's because mainly I'm more familiar with GPU programming, CUDA programming, but more familiar with AMD architecture. So a warp is a group of threads that runs in lockstep. What does it mean in lockstep? That means if they move forward 1 foot, they have to move forward the same foot. That means if they do add operation, all these 32 threads have to do the same add instruction. Okay, lockstep means they just do the same instruction. So I only decode one instruction. I decode it, I issue it, I run that, then 32 operations are performed. Okay, so really low overhead on the issue side and really high power on the compute side. Then the number of warps means different things. Then just 32 thread on NVIDIA, 64 thread on AMD GC and CDNA GPUs, and on newer AMD RDNA GPU, they could also go back to 32 thread. Okay, there's some design philosophy behind 32 or 64, or sometimes we can even propose 128, but there's always a trade-off. Talk about that later. So just do some calculation. So how many warps are there in a block? So if a block, so levels, right? Kernel, block, warp, thread, 4 levels. Kernel, block, warp, thread. Okay. One thread, 32 thread forms a warp, right? 32 thread forms a warp. Then in this case, if one block is 32 thread, then there's one warp per block. And in the largest case, 32 warp per block if there are 24 threads. Okay, simple multiplications, just multiply this number by 32, you get the number of blocks. Warp is a programmer transparent concept. The programmer doesn't really know the existence of warps. That's why I explained it at the architecture side of the teaching, of the lecture. From when we write the program, we only care about blocks. We don't care about warps. Okay, but when you decide warp sizes or block sizes, why you start with 32? You never want to have 2 threads per block. That means you still need 1 warp. In that case, only 2 threads are running, the other threads are wasted. So there's no point to have smaller blocks. So a typical block is like 256, that level. Okay, so but at least never go down with 32 and there always be a multiply of 32 threads per block. That's because the warp is limiting the granularity there. Okay, so threads in 1 warp are bundled together. They always execute the same instruction. And talk about SIMD or SIMT. It's 2 terminology. If you say GPU is SIMD, nobody will really argue with you too much. But if you want to be more precise, people also call it SIMT. What's the difference between SIMD and SIMT? Then I suggested like a CPU also have vectorized instructions, right? So, but CPU works more like in this way. It has most of instructions are not vectorized. Only some specific calculation are vectorized. So vectorization happens sparsely, right? So in this case, we call this instruction a SIMD instruction. In GPU, it's slightly different. GPU works in this way. Every instruction is parallelized. At least the most of instructions are parallelized. In this case, we call this SIMT, so single instruction multi-thread model. Okay, although for most of the time, we don't really need to differentiate these 2 concepts that much.